Okay, well, thank you for the introduction and the opportunity to speak to you today. I was asked to give a brief presentation of some work that we've been doing to develop a continuous flow solar UV disinfection system. And its intent originally was focused on developing countries, but it has application elsewhere as well. So I want to start by acknowledging the team of people that I've had the pleasure of working with, most of whom are listed here and pictured here. All right, so motivations for this. In a general sense, when we consider interventions that have a likelihood of being successful, we generally tend to focus on those interventions that use locally available resources, either human resources or natural resources or both. Among the natural resources that happens to be common in the developing countries where water problems are prevalent are solar ultraviolet radiation. So if you look at maps, for example, that represent global distributions of improved water or spectral solar irradiance, the germicidally active solar radiation, there's a lot of overlap between them. And that was part of the motivation for development of SOTUS, which probably most people in this room are familiar with. This is a technology that's low cost and scalable. It's very effective for control of microbial pathogens. The mechanisms of microbial inactivation are reasonably well known to involve both heat and in some cases some oxygen-based reactive intermediates, including singlet oxygen. And disciplined application of this process has been demonstrated to be effective for reducing disease transmission, which is the ultimate goal. They're also very simple to use, and because of all of those reasons, it's currently being used by something like 5 million people globally. However, there are limitations associated with this process, and as an engineer, we oftentimes try to figure out a better widget. So that's what I'm doing. So that's what we're doing. So among the limitations that are listed over on the right are that this is a batch process, which limits productivity. It's also limited to UVA radiation. And the reason that I mention that is that usually this is done in a PET plastic bottle. This is a transmittance spectrum that we collected on conventional PET film that's used to manufacture those bottles. And you can see that the film itself is essentially opaque to UVB radiation. I mention that, this segment of the spectrum, because it is that segment of the spectrum that is by far the most germicidally active. So this process by itself is excluding the most active part of the spectrum from the process itself. There's also a lack of process control in the sense that it's difficult to measure. You know, the standard is 6 hours of solar exposure, as is sort of illustrated in this schematic that I lifted from the AVOG website. But the problem is that there really isn't an effective process to control. Now, I noticed that in the program there is an organization that is suggesting or perhaps has developed a control box for this. I'd love to have a conversation with them. I have a lot of questions, but nonetheless, there are some limitations that are associated with this. So our objective was to overcome these limitations and to develop a process that would be somehow superior to the original form of SOTUS. All right, so the way that we're going to do this is to use the tools that already have been applied for evaluation, design, development of what I would just term conventional ultraviolet disinfection systems. So my group and other groups have been very active in the development of what I refer to as photochemical reactor theory, really understanding how these systems behave, applying the conventional tools of physics and chemistry and microbiology or the engineering sciences to develop, let's say, efficient ultraviolet disinfection systems. The approach that we're using here is to use those same tools. The physics and the chemistry and the microbiology don't change. The boundary conditions change and the source of radiation changes. But beyond that, we really have the same system to work with. So the approach that we're using is to adapt those same tools that we've used in these conventional ultraviolet disinfection systems and to use them in this somewhat unconventional approach. We want to increase the throughput that's possible with conventional SOTUS. We want to develop scaling relationships so that we know how to design these things at essentially any size. We want to develop process control. We believe that's possible, and I'll show you how. And our intent is to develop these for both community scale and point of use applications in either developing countries or developed countries. So I'm showing you two different forms of these reactors. The first one that's illustrated over here is based on a geometry called a compound parabolic collector. The second one is using a Fresnel lens, and both of those accomplish essentially the same objective. All right, so if we consider just kind of the fundamental photobiochemistry that's responsible for the behavior of conventional ultraviolet disinfection systems. And what I mean by conventional are those systems that are using so-called artificial sources of ultraviolet radiation, usually UVC. These are usually generated from mercury lamps or something like that. So because of the chemistry that I'll describe in just a second, these processes are broad spectrum, meaning they can go after a wide range of microbial pathogens or microorganisms in general, whether they're pathogenic or not. It includes bacteria and protozoa, and there was a comment that was made earlier about the lack of effectiveness of chlorine against organisms like Cryptosporidium parvum and Giardia and other protozoan organisms. That's really the primary motivation for the use of UV and now in drinking water treatment. UV is generally less effective against viruses than other disinfectants, but there is antimicrobial behavior against viruses as well. The mechanism is very well defined. It involves damage to nucleic acids and proteins, and there's a number of papers that are in the literature that describe this chemistry in gory detail, so I won't bother you with those details. And among the advantages of these systems that motivate their use in developed and in developing countries are that there's minimal effects of the process on toxicity, and that's largely because there are few, if any, disinfection byproducts that are generated. So there's always a balance in disinfection between the byproducts and the microbial inactivation, and this technology happens to have a favorable balance when those two things are considered. So what I'm illustrating here is what's known as an action spectrum. This is a spectrum that illustrates relative activity against DNA. I don't know whose DNA this is, but the idea is that this is fairly generic in terms of describing damage to DNA by radiation in the UV portion of the spectrum. If we consider only that portion of the spectrum that is available outside on a bright sunny day, it's somewhere between 290 and 320 nanometers. So that's the portion of the spectrum that we're going to focus on and try to take advantage of. If we consider also the radiation that's available, this just illustrates a simulation that was conducted by one of the models that we use for radiation that's available. This happens to be at altitude in western Kenya, very close to the equator. You can see that we start running out of energy when we get down to about 290, 295 in terms of this. That's the shortest wavelength that we're going to have available to us. And as we go toward longer wavelengths, there's more and more energy available. But again, as we go toward those longer wavelengths, it's less effective. So we have a balance to strike there as well. So I'll start by just presenting some data that we've generated using a device called a collimated beam. The advantage of a collimated beam experimentally is that the radiation is imposed essentially perpendicular to a surface. It is, if it's collimated, that means it's all going in basically the same direction. The only reason that we do that is then it's easy to quantify the dose of radiation that's being delivered. So we can perform these experiments over a range of doses, and we can look at the inactivation response of essentially any organism you want if there's an assay that's available. So here are some data that we've developed for an organism called Salmonella typhi LT2. So this is very closely related to the organism that causes typhoid fever. It just happens to be a non-pathogenic strain of that particular bacterium. So we're working with that organism for obvious reasons, but we hypothesize, and others have hypothesized, that because they're so closely related to the pathogenic strain, that the behavior that we're observing here will be representative of what we would observe in terms of the organism that actually causes typhoid. So here is the measured inactivation response that we've collected over a range of wavelengths using essentially monochromatic sources in my lab. And I've superimposed on this same graph that same action spectrum for the portion of the spectrum that we're working with. And the point of this superimposed data set is that it tells us something about the mechanism of inactivation. What it suggests is that the damage that's being caused across this entire range of wavelengths is damage to nucleic acids. And what that means is that this should be effective not only against LT2, but against a whole bunch of other organisms because they all have nucleic acids in them. So again, the mechanism is DNA damage or nucleic acid damage more generally. That suggests broad antimicrobial efficacy against the same organisms that conventional UV systems are effective with because it's the same mechanism. So we expect effective inactivation for bacteria, protozoa, and to a lesser degree viruses, and we've been able to demonstrate that so far. Some other modeling that we've done, this was for purposes of design of the system. So this image here is a cross-section, and this is a different cross-section of the system. This is using what's called the discrete ordinate model to simulate the irradiance pattern within a particular geometry of a reflecting or collecting device. So this is a so-called compound parabolic collector, and what it suggests is that this device is amplifying the ambient solar signal by about a factor of 5. That means we can reduce the exposure time by about a factor of 5 relative to what you would accomplish by just having the water out in the open. So we used that approach and some other numerical methods to actually come up with a design for prototypes that we've tested. So here is one of those prototypes that was built using the same approach that's used to build boats. So it's a relatively easy method to apply, and these things are fairly inexpensive to build as well. So the general sense or the general approach that we're taking is that, again, we want to amplify the ambient solar signal. There's lots of different ways to do that, one of which is the compound parabolic collector. And then what we're going to do is pass water in a controlled manner through the area that has the amplified radiation in it. So in the case of a CPC, if you look carefully, there is a UV transparent pipe located in the focal area of this CPC, and we're going to pump water through that area to accomplish disinfection. The other geometry that we're working with is called a Fresnel lens, and the basic idea here is that we're taking radiation from this large lens and we're focusing it down to basically a spot, and the geometry of this particular reactor is such that it promotes plug flow. We also have a phenomenon called total internal reflection, which is the same physics that we take advantage of with fiber optics. And the benefit of that in this case is that it allows us to use all of the radiation. It's all absorbed by the water rather than only a small fraction that we get in conventional systems. So we believe that's going to allow for the development of a very efficient system. We've done testing. These are testing based on E. coli as the challenge organism, but we've used several other organisms so far, and we have plans to do others. So I'll just kind of walk you through quickly what's represented here. In the top panel, on the vertical axis is base 10 log inactivation. It's the fraction of the population that's been inactivated, expressed as base 10. The horizontal axis is just time of day. So we collected samples at several different times of day, and you can see the incident pattern of radiation that was being measured simultaneously at basically the same site. On the right vertical axis of the top panel is the so-called DNA weighted dose. So we can calculate the dose of radiation based on DNA weighting, and you can see that the weighted dose in black tracks very well with the inactivation response that we see for E. coli. And in fact, if we look at a larger data set, what we see is that there is excellent prediction of microbial inactivation based on this DNA weighted dose. DNA weighted dose is something that we can measure in real time. We can calculate it in real time based on real time measurements. So we have a control parameter that we can use to monitor and control the behavior of this system. A couple other aspects of the system that we now understand and that we're continuing to explore are the wavelengths that are particularly important in terms of accomplishing microbial inactivation. Here what I've done is on the same graph superimposed that same DNA action spectrum that I showed you before and several spectra of radiation which were measured on the days of experiments that we conducted using one of the prototypes. If you multiply those two things together, you get what's called an effectiveness spectrum. An effectiveness spectrum basically tells you which part of the spectrum is doing all the work. So the larger the value, the greater the representation by that portion of the spectrum. And what this tells us is that the vast majority of microbial, E. coli inactivation in this case, is being accomplished by radiation between 300 and 310 nanometers. Again, that's important for us to understand how to control this system. What we need to do is to measure radiation from that portion of the spectrum because that's where most of the work is being done. So again, we have a pretty good understanding of how the system is going to behave, both in the lab and in the field. And so that kind of leads us to additional work that we're conducting now and that we plan to conduct in the future. So we're doing quite a bit of numerical modeling. I showed you a little bit of data from the SMARTS model that is available. You can download it on the web, and TUV, another model that you can download from the web. These are both models that allow us to pretty accurately simulate spectral irradiance at any location, meaning latitude, longitude, altitude, and based on atmospheric condition, time of day, all of the parameters that are likely to be relevant with respect to available spectral solar radiation from the sun. So we've been able to demonstrate, we and others have been able to demonstrate that the predictions of these models agree well with instruments that are out there to measure these parameters. So we think we have tools that would allow us to explore the applicability of this technology pretty much anywhere on the surface of the Earth, or elsewhere for that matter. And there's other models that we use very conventionally for design of so-called conventional UV disinfection systems, and what we want to do is to adapt, for example, computational fluid dynamics and irradiance field modeling, that's this thing down here, and ray tracing for purposes of simulating the performance of these systems so that we can optimize their performance and design a better widget. So these are, again, being used for reactor design and optimization, and we're really adapting this from approaches that we've used with conventional systems. So our next steps are to evaluate the effectiveness against microbial pathogens. So I've described some work that we've done with E. coli and with some other bacteria. Our plans are to evaluate other bacteria. We want to evaluate the effectiveness against crypto and giardia because those are important protozoan parasites that are, we hypothesize, because of this mechanism we've described, should respond favorably to this approach. And we also would like to explore the behavior of viruses. We're planning to characterize spectral irradiance using the numerical simulations that I talked about, and there's a method that we've developed called local actinometry that allows us to do measurements of this at very small locations within the reactor system itself. We're working on sensor development. We're also working on materials of construction. So I had actually a meeting yesterday with representatives of Lucite, and I have had conversations with them prior to yesterday about how we could adapt some of their acrylic materials that are now being used, for example, in tanning beds. By the way, this is not intended as an advertisement or support for tanning beds. I would, in fact, go the other direction and suggest that you not do that. But the materials that are used there are intentionally designed to be highly transmissive of exactly the radiation that we're interested in. And by the way, the damage that we're doing to microorganisms is exactly the damage that would be done to your skin in these devices. So again, don't go there. But there's productive applications for these materials, and they're very interested in working with us to have these things manufactured in the geometries that we're interested in for these applications. The reflective material that we used on our compound parabolic collector was aluminum foil, literally, that we bought from a grocery store. So it turns out to work reasonably well, but there are other materials that are more reflective of the radiation that we care about. So one of those materials is called metallized plastic film, and you might be more familiar with this if you look at the inside of like a potato chip bag or something like that. That's what these things are made of. These are metallized plastic films. And my point in suggesting that you look at the inside of a potato chip bag is that these are very inexpensive materials, and they have reflectivity of about double what you can get from conventional aluminum foil, which suggests a potential improvement in the performance of our system because we'll be collecting more radiation. So we want also to develop scaling relationships. We think from our work with other conventional disinfection systems that we have a pretty good handle on how they work, how they perform. And from the work that we've done with these specific applications, we also believe that there are scaling relationships that can emerge to allow us to take the prototypes that we've developed and translate that to something that would be a practical application. We plan to use numerical simulations, and here's just a very quick illustration of such a numerical simulation that we've done on a conventional UV system. We plan to evaluate the effects of cloud cover. We have done some experiments to examine this, and clearly cloud cover will play a role. We want to be quantitative in assessing the effects of cloud cover. It's not an easy problem to solve, by the way, but we have ideas about how to approach that. And then lastly, we want to implement this both in developing countries and developed countries. And the developed countries strategy is really from the perspective of if we go to developed countries where there's likely to be more financial resource, that might be a strategy that we could use to develop this technology to the point where it could also be implemented successfully in developing countries where there's less resource available. So it should accomplish the same objectives in terms of disinfecting water, regardless of the location, but we think there may be a financial benefit to going to developed countries as part of this plan. So anyway, those are the comments that I wanted to make for the time being, and I'd be happy to try to answer questions as part of the panel, I guess, that we'll be convening now. Is that right? Okay, thank you.